So if we start by looking at purine synthesis, we know that our purines are composed of a bicyclic structure, and it's synthesized from carbon and nitrogen donated from various compounds, as we talked about earlier. The synthesis starts with the synthesis of our activated 5-carbon sugar, PRPP. And we've talked about this reaction catalyzed by PRPP synthetase. So what's important to note about purine synthesis when we compare it to pyrimidine synthesis is that the synthesis of the ring structure happens on our 5-carbon sugar. So the initial step here involves the synthesis of 5-phosphoribosylamine using our substrate PRPP and glutamine. Our enzyme here, PRPP glutamyl amidotransferase, is our regulated and committed step in purine synthesis. From here, we continue to add nitrogen and carbon groups to build our bicyclic ring structure. Our substrates, again, are glycine, folate, as well as aspartate and additional carbons from folate groups. You'll also notice that ATP is required for these reactions. Oh, and let's not forget glutamine. So beyond knowing the donors for the synthesis of our ring structure, there's not much in this intermediate part of the pathway that we need to focus on. It converges on the synthesis of inosine monophosphate, and inosine monophosphate is characteristic of our base hypoxanthine. So this IMP is going to be used to generate both AMP as well as GMP. So the conversion of IMP to GMP and AMP is noted here. What's important to note is that the synthesis of the base, let's say AMP, requires the reciprocal nucleotide as an energy source. And by that I mean to convert inosine monophosphate to adenosine monophosphate, we need GTP as an energy source. And the same is true for the conversion of inosine monophosphate to guanine monophosphate. We need ATP as part of this reaction. This allows for the maintenance of nucleotides in a relative ratio that is required for cellular processes. The generated nucleotide monophosphates can then be converted to the di- and triphosphate forms by nucleotide-specific kinases, which will transfer phosphate groups to maintain a balance, again, of the mono, di, and triphosphate forms. So the key regulations of purine synthesis are illustrated here. We've talked about the regulation here of PRPP synthetase by our purine nucleotides. So elevation of our purine nucleotide bases will inhibit the conversion of ribose 5-phosphate to PRPP. The second notable regulation here is at our committed step by PRPP glutamyl amidotransferase. This enzyme is also inhibited by purine bases, and that includes inosine monophosphate as well as AMP and GMP. So in addition to those two regulatory reactions, there's regulation of the conversion of IMP to AMP and GMP. And what we noted is that the reciprocal energy source is required for synthesis. So ATP is required for the synthesis of GMP, and GTP is required for the synthesis of AMP. You'll also note that they regulate their own synthesis through feedback inhibition. So GMP will negatively regulate its own synthesis, and AMP will negatively regulate its own synthesis. And again, this is really so that we can retain a relative ratio of these nucleotides. So that's a really large overview of purine metabolism. But I want you to focus on the regulatory steps here and our intermediate inosine monophosphate, as that'll be important when we talk about purine salvage. Which leads us to our final question, which is an elevation of purine nucleotides we've seen will inhibit synthesis of purine nucleotides. And what we'll notice in the next discussion is that it'll also negatively regulate pyrimidine synthesis. And it does this by, again, inhibiting the activity of our regulatory enzyme for pyrimidine synthesis, and that's carbamyl phosphate synthetase 2. So we'll follow up with pyrimidine synthesis in the next discussion.